warm up, and this warm up will be on the next thing. Every one of you have your own computer at home, yes? And on previous hour class we have had small analysis of top 500 computers.
Yes.
You saw the most powerful and high performance computers in the world. We didn't talk about the cost of these computers, but we talked about configuration, about architecture and operating systems which are used in these computers in general. It's not something complicated, something theory, but the question, how you can compare your own home computer with these computers from top 500 computers? What criteria you have to use? What criteria? How you can measure performance of your computer and compare your computer which you have at home and these computers from this list? How you can do this? And you can do this in a very simple way. And this way was, and this approach of measuring and comparing, this comparison based on using of one package, software package, which called Linpack. Let me show you. We have at first at official site of Intel. We have download benchmark. This benchmark is available for multiple operating system. It is Linux, Windows, Mac or something else. And what we have here? Here we have, this is a license. Okay, we accept this license. And sorry, internet is a bit slow. And on this page, just a moment, and also we have Linpack, and then I'll also show you another one, Linpack, because how many students have, whom of you are using Intel CPU? You know, Intel. You have laptops, maybe. Intel CPU, how many students have? How many students have AMD? You, yes? So you distinguish CPUs from AMD and Intel. There's some introduction. I want you also. Okay, where is this? Just a moment. Linpack. Okay, let it be this, and also we are interested in the Linpack. You see how we write it? Linpack. The main purpose of this Linpack to benchmark your computer. Also, we have Linpack Extreme. Linpack Extreme you can use for both, for Intel and for AMD CPUs. So if you have AMD, don't use Intel Linpack, use this Linpack Extreme. Because when you start in your maybe let's play with this model which is for both operating system, both operating system. We are talking about this. Oh, it's too slow. We are talking about so if you visit official Intel site, you can download this table, this one. So here at this table you see that you have multiple Linpacks. Linpack for Windows, for Linux and different versions. With our students we also tested that you can simply use this oldest version, because in the newest version there are some issues with dependencies on the libraries. You have to install previously some library, but these packages for Windows, for Linux, for macOS can be used only by itself without any additional libraries. So simply click here, download this archive, unpack it, and run it. Rather simple. I'm working on a Linux, so just a moment. Also, it's still loading. Download, and I downloading this. Okay, first I show you how it looks like at I have also downloaded them. You see, we have LMKLB. This is a key. You see this? You see. In your Windows, you will have environment where you click with the right mouse button and do this. If something is not clear for you, please ask me and let me know. My suggestion for you, if you don't have experience with the Linux, I suggest you to try to acknowledge with it and learn it. But it's not for this laboratory work. You can use Windows without any restrictions. So we have benchmarks, yes, and we try to do this. And what you have to do, we have few files in this directory. We have to run me Xeon 65 or file. And also we have a lean input Xeon 6564. Sorry. What is this? Lean this file is the configuration of this test. What is the idea of this test? Idea is using of solving systems of linear equations. You had experience with resolving these equations in math. Systems of equations. Systems of linear equations, because there are linear equations and non-linear equations. So you have x, you have equals to y, multiple, it's a system, yes, and you try to substitute different components. A method of Gauss method. At least you have to remember that you have had something. Maybe you do not remember how to do it right now. Remember that you haven't do it by yourself, by your hands. Simply you have to know that this program based on this method and using it inside it. So what you are doing, let's look at this file and let's analyze what this file is. So we have lean input Xeon 64. What inside this file we have? Inside this file we have, okay, let me show you at first what we have. Original file looks like this. This is the original file. We have 1, 2, 3, 4, 5, 6, 7 lines of the code, and this is the configuration. We have 15 number of tests, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes? So these for each of these tests we have problem sizes. The size of these equations. Oh, sorry, equation, not equations, but equation. But no, in general it will be equations because multiple tests. And our library with random values, because these values in these equations will be random at the beginning, try to resolve these equations. And also we have to obtain average results of our tests. We have times to run this test. How many times we need to run it. If you have not high performance computer, if it's regular laptop, what we are doing? We decrease this number and also we reduce these values in this line. Simply, it's text file. Edit it, remove these files. But be careful with the numbers. So if you, for instance, reduce this number to what we have this, and what I'm doing, how I prepare this for our case. Number of tests. Okay, I left it as 15, but problem sizes. This times to run. These values should be the same. Left it the same. So I left only 4. It will be four equations. This equation, this, and this. If your laptop has work on batteries, remember that you can, and you don't have power supply, your computer can drain your battery, because it will CPU will be really compute something, and you will hear about from the fan in your coolers, and etc. You will hear from your computer that it's working now. For simplest cases like here, we will not hear something strange, but let me run this test. In Windows, you will run exe file. What I'm doing? 64. Yes. Run me. Xeon 64. And we start this. You see this test. It's calculating now. Yes, and yes. But also in this case I have to reduce this value 1, 2, 3, 4. I have to put here value 4. Let's do it again. Because in this case I have empty lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you see, yes, 15. Why these empty lines? Because this test, so it was incorrect, yes. Now it's calculating. Yes, done. Also, okay, because you may ask, 5,000 and 15,000. Okay. Let me show you additional, a bit complicated option to see that this computer works really. But I'm on a battery. On a battery without. I have power supply. Yes, I have power supply. Okay. Let me show you in also this case. 2 and 4. Save. Also, I start additional terminal, and here I start program with the name htop, which shows me load of my cores of my CPU. Yes, you see, 1, 2, 3, 4, 8. And let's start test. So again, it's working now, and you see that all the CPUs. 108 4 CPUs. Why 4 CPUs in 100%? Because here we have physically 4 cores and 2 threads per 1 core. You know, and you understand what it means. I believe yes. Architecture of CPU. We have 2 threads per 1 core. So that's why we have only 4. It will not be efficient to load additional threads. But this is Intel processor. And also Intel library. We also have another library, and it's calculating now. You see, it takes some time, really. And if you look at the temperature of if I look at the temperature of cores, I can see, and CPU, I can see that the temperature will be larger. Maybe in this class is not hot, but in your regular case, in your room, maybe the temperature will be higher of your CPU. So yes, done. So let's analyze what we have here. We have performance in gigaflops. Gigaflops. This word, flops. What is the meaning of flop? Do you know or not? Flop, this. F-L-O-P-S. Maybe you have heard about it or not? No? Or? Okay, and also we have here values, different values. Yes, and you can estimate and measure the average. So let's analyze and let's understand what is meaning, and also let's start to play with AMD test or universal test. Linpack Extreme. AMD. Let's run this test, but first let's analyze settings. Problem size is this. Okay, let's try to play with it. Run benchmark. And you see the same. Yes. Now what about flops? At first, flops, the meaning of this word is floating operation per second. So how many floating operations per second do you have? This is the flops. If you have giga, peta, theta, tera, mega, you have thousands of thousands, millions. You got idea, yes? Floating operations per second. Another measure you can have, it's million operation per second. So we have one measure is a metric, is a flops. Another one is a MIPS, MIPS. In this case, we have floating operations. In this case, we have simple operations. The test is running now, and I don't want to. Okay, let's. It's finished. It's finished. Oh, but 8 minutes. Now I understand why my computer ran out of my battery. So what we will do now? We will continue talk about small introduction to parallel computing, and In previous our class we finished with the this was small warm up, not only for my computer but also for you, how to test and measure your computer. And I want you not only write program with the matrices and calculate it, but also try to download this package and test your computer, your own computer. It's not something complicated. So first your laboratory work, I want you to write matrix multiplication, addition, or etc. I wrote this task in our distance learning course, and also try to test your computer with this test. You asked me about how to done it. How to make a report, submit. If you want to tell, you can. Yes.
What we submitted the assignments, just like we've done the assignments like matrix multiplication and addition.
Previous our class, when we have this class, I wrote in our distance learning course, in this lab, I wrote names of the students and wrote what things you have to do. So this is your simply print code of your program and results of this test. That's all. Very simple. Very simple. So okay, and results of Linpack benchmarks. So we do this, and now we continue with our course, and we talked about previously. We talked about I also promised you to show server. Okay, so on the next Monday, please remember me. Because it's not something complicated. If it will not be something with the snow, frost, then. So you see here that we have different tasks. You remember we talked about it. We talked about architecture. Yes, we finished on architecture, I believe. So single instruction, single data. This is for a human computer. Single instruction, multiple data. Multiple instruction, single data. Multiple instruction, multiple data. Nowadays, we are talking about two architectures which you saw in top 500. These top architectures, these architectures are, first of them is cluster architecture, and second one is MPP, massive parallel processing. What is the cluster? The cluster is the group of computers connected by a network and resolving one or few tasks system. So imagine that you connect multiple computers and you have something like one large computer, large PC. At the end of our class, I will show you the simplest way how to test it and how to play with it at home. The simplest way. It will be a bit outdated, but in my opinion, it is the simplest way. So you can blame me, oh, this is old software, old, it's not modern. Okay, but in this way you can step by step run multiple two computers like the whole. And you haven't to configure IP addresses, ports, and playing with the libraries. So it will be very simple toy example. But it will be enough, and I believe you have to spend some time playing with it. So a cluster is a group of computers. Also MPP, I will frankly tell you that it's like a cluster, but MPP is a cluster with special network connections. What it means? It means that connections between nodes or hosts of these computers will be will have a higher throughput than ordinary network channels. For instance, if in cluster we are using something like Ethernet, I'm talking about 10 gigabit Ethernet, okay, also it could be gigabit Ethernet, 10 gigabit Ethernet, 20 gigabit Ethernet, 40 G, it also could be InfiniBand. It's specific computer interface, very specific, rather expensive, but in this case you have very very high throughput. It's like very close to memory access. So two computers can access to each other like it's not the same, but like to the memory of you understand that access to the memory, random access memory, is the fastest way of communicate inside your computer. But imagine that you have two computers, and in one computer you have to calculate values which you have in another computer, in another one. What you will do? You will simply connect to this computer through the network, yes, and read this data and write the data. So in our case, the performance of our computations depends on this communication. That's why we are using not we are using, but in this architecture used some specific technologies, memory channels, etc. There are multiple technologies, but now we have to know that these are Ethernet. Here you have something very specific. But in any case, technologies based on Ethernet, InfiniBand is not Ethernet, sorry. You have to understand that this is not Ethernet, InfiniBand is not Ethernet. But here we have something special. And now we continue with another things. Let's talk about things we have. What another things do we have? Okay, maybe you have some questions or ask me. Some words you don't understand. If you talk, you can.
Most of these processes we use matrix for most of them. We use matrices for most of what we are going to do.
For test them. Matrix, yes. Indeed, if you're talking about Linpack, yes, the name of this test, Linpack, it's the name of linear algebra. And if you're talking about matrix multiplications, yes, it is the simplest case which we have in linear algebra. Sure, you're right. I can suggest you to resolve system of linear equations. But I believe it will be more complicated than working with the matrices at the first class. In the next other classes, but you are it's a very good question, because in our next classes we will have libraries, specific libraries, which you can use for matrix multiplications, for resolving systems of linear algebra. And what is the name of this? It's BLAS, Linpack. This is the names of libraries, Linpack and BLAS. Basic linear algebra subprograms. You see? Here, what here we have? Do we have? In our next classes, I suggest you and show you how to do it. Use this library to resolve these systems of equations. Simply write program, very simple, and execute it and show the result. See the result. Also, you have to understand that these programs have internal technologies to decompose the task and distribute this task between your cores, your CPUs, and your computers inside these libraries. So we have multiple different tasks, and for instance, linear equations. Okay, let's click on it. We have some general representation of linear equation, and we have, these are the names of functions. You can calculate it in single precision or in double precision. You know that we have float and double. So single and double precision. You have to understand that float precision in any case will be faster than double precision, because right, absolutely right. You have the size of the amount of your data will be less. Also, very important for you, if you decide to continue your education somewhere and go to the master, but I'm talking about real master, yes, and you interested in the most cutting-edge technologies nowadays. It's artificial intelligence, yes. Technologies of artificial intelligence, it's machine learning and deep learning, two technologies, because artificial intelligence comprises deep learning, it's neural networks, very complicated neural networks with the complex architectures with multiple neurons and multiple layers. And we are talking about machine learning. It's classical methods of statistical processing, game theory, theory of optimization, etc. But all of these things inside using oftenly used tasks of a linear algebra. I'm talking about simple calculations, because usually in your computers you're working with the vectors, and or you're working with the matrices. Yes, for instance, you can represent some values like a matrix of values. Also, you have text. You convert this text to numbers according to some algorithms. There are methods, and try to do something with this text. But again, you are working inside. Usually, you will do this, playing with the vectors, finding average, max function. But you are playing with the vectors. You find dot products. Usually, you will not do it manually, but libraries you are using do it for you. And usually technologies of machine learning, artificial intelligence, deep learning, they are nowadays usually they use also clusters, but these clusters are based on GPUs. So you have, for instance, one computer with 4 or 3 or 5 video cards from NVIDIA with about 11 gigabytes or 8 gigabytes, depends on the money you have to buy a computer. And these video cards are using not for playing games, but for calculations. And if it's not enough for you to have performance of one computer, you buy another node, connect them together and try to resolve in distributed environment. But also these video cards internally resolve the same tasks. And it's also linear algebra and etc. But it deeply inside. For instance,
what makes a GPU better than a CPU in terms of calculations?
In the purpose of learning, you can use CPU, but in real world, usually you will use GPU. And for purposes of machine learning, artificial intelligence, usually nowadays use developers and data scientists use these technologies. Graphical processing unit, because CPU is too slow. And also for GPU computations, it is too expensive to use double precision, a newer version of these graphical processors using single precision. So because also we have evolution of these graphical processor units, which are now not oriented only on the gaming, but they are oriented also for these computations. That's why, for instance, NVIDIA, and not only NVIDIA, but another vendors, it's AMD. Only 2 vendors nowadays in the market. No, not only, but these 2 vendors have libraries for neural networks. It's specific libraries which optimize computations for these purposes. But internally, they're using these calculations. Because for you, from the point of view of higher, yes, you see only the neurons, but internally there are functions like softmax, attention mechanism, and etc. And inside this mechanism, you are using this basic. It could be multiplication of scalar by vector, multiplication of matrix by scalar. So it's one number which you multiply on one matrix, and etc. So this is what I talked about. Okay, so these are the libraries. It will be further in our course. But okay, we have this architecture, and MPP and cluster belongs to this architecture. But if we are talking about video processing and graphical processor unit, we are talking about single instruction multiple data, SIMD. This is for this is a category. This is a category which you can use to classify all the class of graphical processor units. But it's a vector processors. But important to know and understand that these computers connect together, and also they become MIMD. So from one point of view, from point of view of one node, it could be SIMD, but so we had talked about these technologies previous our class. I promised you to show this. Okay. Also, we talk about some speed up, granularity. Okay. What are the main characteristics? Yes. We have to take into account what metrics we have to take into account and terms we have to use when we are talking about computations. Terminology, yes, some general parallel terminology. So supercomputer, high performance computer. It's a very abstract term, but you understand that this is some computer which nowadays resolving some tasks with a higher speed than your computer. This is a supercomputer. Node or host, it's one computer in this cluster. CPU, socket, processor, core. This is different computation units. Usually CPU is, you acknowledge with CPU term, central processor unit or processor or core. Core is a part of CPU usually. If it's single core CPU, then it's one core equals to processor. A task, a logically discrete section of computational work. So if you have, we can have a large task which you can subdivide into subtasks. But logically, it's a discrete section of computation work. You see, parallel program consists of multiple tasks running on multiple processors. So you can have large task, you subdivide it into subtasks and run this in parallel in multiple nodes, in multiple cores. Shared memory. Shared memory is a technology when we have multiple cores and we have one amount of memory, the whole memory field. So this is shared memory. With this term, we also have symmetric multiprocessing. These terms, shared memory and SMP, is very close. They are close together. Why? Because I don't want to draw it, but maybe I do it in this. Sorry, graphics. We have this one. So what we have? We have one CPU. Maybe I change the color. Maybe it's this. Oh. This one. And so four CPUs or 4 cores. Or if you want, it could be into how to put into the back. I don't know how to do it, but okay, maybe nevertheless I will do it this way. In this case I will do it in this way. And what I do now, imagine that this is one CPU, this is another one, and these are cores inside the CPU. But this is the whole computer. We have one single computer. Computer will be red. This. Now it's sorry. So these are CPUs, and these are the cores. But also we have here memory. Memory will be yellow. And what is the meaning shared memory? That means that this memory is shared between all of these CPUs or cores. So this memory is shared between them. And for these systems, indeed, usually it is simpler to work with this technology than with distributed memory. And now, so this is shared memory. Memory is shared between all these cores. You have to remember and understand, because when we will work with technology OpenMP. It will be the first technology we will learn. OpenMP, Open Multiprocessing. And it is sounds like very close to SMP, yes? Symmetric multiprocessing. Why? Because we are talking that all of these processors are equal in the access to this memory. All of these cores of these CPUs can access this memory in the same way, in the same manner. Yes, we have some disadvantages in this way, because you can have conflicts, and there are another problems you have to resolve as a developer. But it is the simplest way to program and to run program. You write data, for instance, something which is executed in this core, write something into the memory, and another core simply read this data. That's simple. But imagine that you have this is shared memory, yes? But if you have distributed memory, in this case, you have also network connection between these hosts. I don't know, you see this? Yes, it's visible. So we have network. And in this case, program from this computer will try to get some value which you store in another computer. Yes, when we will write our programs in our classes, we will use libraries which simplify this work. If you know C language, and if you know the general paradigm of technology that we will use, it will be simple. But from this class, you have to remember that this is the system with distributed memory, because we have two nodes, and you have network communication between these two nodes. To get memory from this node, you have to access to the network and read some data from the memory of another computer. It's the memory space of another computer. It's a bit more complicated. So this is distributed memory, but if you are talking about one node, we are talking about shared memory. So this is the idea. Shared memory and distributed memory. And SMP, all of these CPUs have the same rights to access the same to data which are inside this node. And if you're talking about SMP, again, SMP, we are talking about one computer. This is SMP.
So basically, SMP means like this CPU has the same number of cores as this other CPU, system. If there are two CPUs in a computer now, so this one, let's say for instance, one has 4 cores. This one has to have 4 cores. That's how you mean?
What I mean, in general, for yourself, you have to understand. I believe that your computers at home have multiple cores, so you have SMP system. That means that imagine that one CPU has unequal access to this memory. What it means? It means that one CPUs have faster access to the memory and another have slower access to the memory in one machine. But usually nowadays you are using
So I don't understand. You said one has faster access to memory, and the other one has slower access to memory.
in this case, if someone has faster access than the other one, in this case you will have
It's no more symmetric.
yes. Okay, it's clear now for you. So symmetric. Okay, let's continue. Distributed memories. Communications is also clear. And the second, if you're talking, okay. Communications. What about communications? That's about networking, some bus or something else. It's also when we talk about all communication equipment. Synchronization. Synchronization, as you see, very often associated with communications. But I want to explain you it in the simplest way. What about synchronization? Okay, now we go back to this picture. Imagine that we have in our memory some value with the name sum. You can guess that this value is simply sum of some values, but it will be sum of the result of some calculations, or maybe it could be average or sum. And you have one task, second task, set task, and additional task here, force here. You see this, yes? I draw these three curves in the arrows longer than force one, yes? Why? Imagine that this is the time of execution or speed of execution. Imagine that you have at the beginning all of these something Indeed, in computation we will talk about threads. We will talk about thread, computational thread. And these are computational threads. But imagine that each of these threads calculates something. And imagine that the amount of data for this thread was larger than for other threads. And there is some point in the time when you calculating, for instance, this line, green line, when you're calculating sum, not this, but sorry, this line. For instance, this line. Here you calculate sum, and in this case you will calculate the sum of only of these three values, but you will not take into account the value of this processor. This is a problem. And you have to understand that in all parallel systems, I want to tell you this in the first class, this is the rule, in any parallel system, distributed or SMP system, you will have unpredictable time of your of the order, you will have unpredictable order of your task's execution. You can have the same program and you can have 4 or 10 threads in 2 or 1 computer. You run your program, and in one case these threads could be executed 1, 2, 3, 4. In another case 3, 2, 1, 4. In another case 2, 4, 3, 1, and etc. So you cannot predict the order of execution. And in this case you have to make something which oblige these threads to wait for them. So you have to please do not calculate the sum while all of these threads not calculate. You will not obtain the result of all the threads. That's why we have to use, this is very important. So I will show you this in the next classes. So that's what we are doing. So in any case you will not have, you cannot predict the order of execution, and some of these threads can finish their work faster, another one can do it slower. This is one problem. And another problem, you have sum, and how look like from programmatic point of view summing operation, what you are doing. You have A plus B equals to sum. Imagine that you have to increase the value of sum. This is okay. You have some, maybe okay. In our computer, we declare some value, sum, yes? Then thread 1 has some result. Thread 1 has result 1. And you want to add this result to the sum. What you're doing? Very simple. At first operation, this thread read the sum. At first you have to read sum. Second step, you R1 plus sum and then you have to write sum. to some shared memory. Yes, and imagine that there is another thread. And what you're doing, you also read the value, you add, and you write some. So the question, imagine that the value sum is shared between these threads, because these threads are executed in the separate cores or CPUs. And imagine that at some point one thread read this value, second one read this value, obtain the sum, add this and this, and first write result and second write result. But this thread have to take into account the values from T1 or T2, yes? So you see that at one time slot or time frame could access only one thread. This is like a window in some office when only one person should put its documents or something else. So you have to limit this. And this is the task which is resolved by synchronization. This is synchronization. This is synchronization. Here I draw you the figure with the idea. So one problem is that if you don't wait for all the processes, you don't make something which is called barrier synchronization, you will not obtain correct result, yes? And also I show you another problem when you have another problem with the improper result when you read the same value, add, but write at the same time. For instance, you have 2 and you have for instance 2, yes, and here you will have 3, and some will be maybe 4. So at some point it will be 4, yes, here will be also 4. You add 3 and 2, you have 7, and here you will have 6. So some will be here, you want to write this write 6, and this write after this write 7. So at some point of you will have 6, and some point you will have 7. Okay, imagine another case that T1 was or T2 was slower than T1, and T1 write proper value 6 and T2 write proper value 7. Oh, okay, you have 13. That's okay. So the right answer will be here at this step should be 13, yes? Because 2 threads and you sum. So incorrect result will be 6 or 7.
One CPU, one core CPU cannot make use of. They cannot simultaneously, right?
Yes, no, they do it simultaneously. You're right. Yeah, they do it in a parallel manner. They do it in parallel.
At the same time.
Yes.
Some results at the same time.
Yes, but the problem that it is not equal at the same time. Sometimes you have some shifting, but in milliseconds, in seconds. But in this case, they do it simultaneously. Right? You're absolutely right. And in this case, you have to provide some mechanism which will reduce the amount of these errors and mistakes. How you can do this? Simply by making this value sum It's called synchronization value, synchronized. So we have synchronization here. So that's why we have synchronization. The coordination of parallel tasks in real time very often associated with communications, often implemented by establishing a synchronization point within an application where a task may not proceed further until another task reaches the same or logically equivalent point. Synchronization usually involves waiting by at least one task and can therefore cause a parallel application's wall clock execution time to increase. So this is the idea. What we are doing, we have this value sum, this variable in your program, and you make something like door, very wide, not wide, but very small door. In these doors can enter only one person. So from programmatical point of view, only one thread can access this variable at one point of time. If this thread leaves this variable, another one can access it. And also you have to understand that sometimes, but it's another more complicated task, that sometimes threads can die, hang up, or something can cause with these threads some issues. And imagine that the thread come into this variable, lock this variable, die, and no one can access this program. And in your screen you see that your program hang up. Yes, that's very it's a real problem. So this is synchronization. It's clear for you now? We will talk about it in more concrete examples with a programmatic way of control synchronization, but now it's only for overview. Also we have granularity. It's a qualitative measure of the ratio of computations to communication. Remember previous our class I told you that if we have one computer is faster than another one, and your computer network is very slow, then maybe it's not reasonable to transfer data over the network if the time of communication is higher than the time of computation. If your computer can calculate the values or some result faster than transmission of this data, maybe you will not spend time for communication, but you will not transfer the data to another computer. You will calculate it in your own computer, because it will be faster than send data at this computer and get result back. So I believe that for today it will be okay. In the next hour class we will talk about example of